Okay, so let's take a look. Do you remember from kinetics in general chemistry what an elementary step is? Yeah, it if you have a reaction, um, let's just make something up here. On the way from reactants to products, you don't know what's happening in here, right? It could be, and usually is, two or more different steps to get you from here to here. And the kinetics, we worked through some problems about how to deduce what are the steps. Well, organic chemistry is not much different than that, um, except that there are just a few elementary steps that can be used to define almost all chemical reactions in organic. And we're going to go, and one of them we've looked at already is proton transfer. And we're going to try to expand a little bit on that. This is old stuff. Opposite charges attract, like charges repel. Now that also is a concept that we can apply to partial charges or formal charges rather than just full ionic charges. So what you see there is that first one is a hydroxyl. That's a bona fide negative charge. But the hydrogen on the hydrogen chloride is only a partial positive charge. So we identify those to save us on the trouble of going backwards and forwards between ions and partial charges. We just call them electron rich and electron poor. And also there's another name for that. The electron rich are nucleophiles. That just means nucleus loving. And since we know the nucleus is positively charged, has no electrons in it, that electron-rich species like positive charges or partial positive charges. The electron poor are just the opposite. They're electrophiles. So they're looking for either extra electrons or partial negative charges. So when we look at the curved arrows here, we see that you're going to find the electron-rich side is going to attack the electron-poor side and start to form a bond with that hydrogen. And when it does, it causes the bond to break between the hydrogen and the chlorine. So then you end up with a water molecule and a chloride ion. That's no big surprise in organic or general chemistry. Okay, and where does the tail of an arrow start? With a lone pair or a bond, right? And it ends on an atom, or it can end in the formation of a bond. You can take a pair of electrons and send it to, well, actually, when you send it to an atom, it's going to form another bond if there's already one there. So that's a semantic problem there. All right. So we've got this methanol as an example with our oxygen and a hydrogen bound. So we've got two types of hydrogens here. Three of them are bound to a carbon, and one of them is bound to an oxygen. Which of those hydrogens is going to be the most electron deficient? Now we're talking in terms of electronegativity. Oxygen is more electronegative than carbon. So oxygen is going to be drawing electrons to itself from both sides, from the carbon side and from the hydrogen side. But any other molecule that attacks this one is going to have a difficult time getting at that carbon. It does happen, but it's not probable. So it's going to go for the hydrogens if it can. And the hydrogen that is the most electron deficient is going to serve as the nucleus, or the electron deficient species, and the nucleophile is going to attack that one. So here we have, let's see. Oh, now that we've said that, say we put this ion in the vicinity. Let's see. Let's make it like this, that. This is going to have. It should have two pairs. Okay. And then we have the methanol group with this oxygen and that hydrogen. And this hydrogen is going to be deficient. So we use that little delta. Remember the partial charge, partial positive, partial negative charge. And in this case, this group actually does have a negative charge. And I looked up the proper name for this. I couldn't remember it the last time we talked about it. This is called the azonide ion. That's the proper IUPAC name for it. If you just take an ammonia and strip a hydrogen off of it, leave the electrons behind, that's what you get. So this is the nucleophile, because it has extra electrons, and they're looking for an electrophile that is looking for extra electrons because it has a positive charge. And what happens is you get these transferred here, and it forms a bond. And then these electrons are transferred to that oxygen. So that gives us this particular anion plus the ammonia molecule. So now we only have one lone pair. Okay. Yeah. So this is a concept from general chemistry. Reactions are always neutral. Overall, when you're looking at it from the outside, you never see an uneven distribution of charge through the matrix, like you do in physics, where you have a Van de Graaff generator and you can produce a nice big zap when you touch it with an electrode. In chemistry, you have to balance the charges. So if you've got something like this in solution, there has to be a counter cation in there. Well, those counter cations are just there to balance the charge. They don't participate in the reaction, and they're called spectators. Right? We've encountered spectators before when we were looking at redox reactions, and you want the net ionic equation. Then you just eliminate the spectators. So whenever you have the alkaline metal cations involved in as part of a reactant, then you can disregard them. You can simplify the procedure simply by ignoring the sodiums, the potassiums, the lithiums. That's all we're saying. So here we have a problem. Let's see, I got that in the way. I can move it out of my way, but it's still in your way. So what we're looking at here is trying to make sense of this reaction between the I don't know what to call that. Potassium. I want to say methoxypotassium. And the other one, of course, is cyanide, hydrocyanic acid or hydrogen cyanide. But when we write them in an equation form, we ignore the potassium, and we just write this one. So this is going to have a negative charge, right? So how many lone pairs are going to be around that oxygen? Typically, when you've got two bonds to the oxygen, you have two lone pairs. But we're missing a bond to that oxygen, so it must have three lone pairs. And we can check to see if that's true. Just calculate the formal charge. Right? How many valence electrons are oxygen? Well, let's see. We have this bond to oxygen and three lone pairs, right, with these H3 like that. So that's 6 minus 7 is minus 1. So that's correct. If we do it that way, then actually we have a better idea. And then we have HCN. How does HCN look? Well, HCN is like this. Okay. And remember, the effective electronegativity can also be applied not just to atoms, but to bonds. So the effective electronegativity here is high for this triple bond carbon-nitrogen. It has a withdrawing effect. So it's going to make this hydrogen slightly positive, and this is going to be the slightly negative side. Okay, so now you have the electrophile. This hydrogen is looking for electrons, and here's your nucleophile. It's got extra electrons. And nucleophiles, they can be charged or they can be neutral, either way. As long as they have a lone pair of electrons, they can serve as a nucleophile. Okay, I found a mistake on that slide. They stuck that azonide ion in there, and it should have been the methoxy ion. Okay, so how are the lone pairs? What are the curly arrows going to tell you? You're going to go from electron rich to electron poor, correct? So we go here to here, form that bond, and then we have this, and then this, that bond there, and this would be but deficient now. This would be C, N, and negative. And we have these, I've left this one out. These two electrons go to that carbon. Okay? So now you get the cyanide ion. So we're trying to ease you into elementary steps with something we've already introduced, the proton transfer. Stop me if it starts to get wishy-washy. All right. Many reactions use what we call organometallics. That just means there's a metal associated with the organic compound, with the carbon, usually. And we can ignore the metal most often. Because what the metal is there for, since metals like to donate electrons, recall that from general chemistry. If you have a sodium and chlorine, throw them together, who's going to lose, who's going to gain? The metal's going to lose electrons, the non-metal's going to gain electrons. So we create these organometallics so that they will give us a nucleophile, in this case, a carbanion. And that carbanion has an extra pair of electrons, which gives it a negative charge. That's the electron-rich species. And when we write them in an elementary step, we don't have to include the metal because we're more interested in those extra electrons to be the nucleophiles. Here's some examples. So you have lithium. Let's see, that first organolithium compound, it would be written without the lithium, and we'd have the lone pair left behind. So how did we get to that point? If we write it like this, right, there's the compound. But in solution, what happens is, well, actually, this is a matter of convenience. I think the lithium is still bound to the molecule, but the fact that it donates its electrons to the carbon so easily, you're less likely to make the wrong assumptions if you tear that lithium away and create this anion, this carbanion. Then it's easier to see the reaction proceed. The second one is called a Grignard reagent. It was invented by a Frenchman back in the early 19th century, I think. And the nice thing about the Grignard is that it was one of the first reactions in which a carbon-carbon bond was formed. Up to that point, reactions that were studied were adding non-carbon substituents to carbon chains, like make alcohols out of them, make sky's the limit. But this one allowed you to make a carbon-carbon bond, and that means you can grow chains and you can make things carbon chains longer. But when we write the Grignard, and this is just one example, any carbon compound that also has, I'm going to put one carbon in here for the effect, has the magnesium here and the bromine here, is very effective at making a carbanion. Let's see. Actually, well, this R can have any number of things attached to it. And this carbon is going to have probably maybe 1, 2, 3 hydrogens. Okay. So what happens is the bromine is an electron donor, right? It's an anion. It's a halogen, a non-metal. So it's going to donate electrons to that magnesium, but magnesium doesn't want them, right? It's a metal. So it gives them up to here, right? And that's where you get this Grignard reagent. And then the organometallics with lithium and copper, having both metals there together, trying to donate electrons is going to produce the methylcarbanion. Brain farts. Those are just some examples of simplification of the reagents. Okay. Do you recall what a reducing agent does? Remember when we talked about, well, in organic chem, not in general chemistry, a reducing agent, when we talk about oxidizers and reducers. So we have, say we have this one is the oxidizer. and this is the reducer. They always go together, remember? And excuse me, start over again. This is the one that is oxidized. If it's oxidized, it loses electrons, right? It loses electrons to B, and this is reduced. Okay? So when that happens, the one that's oxidized is the reducing agent. And the one that's reduced is the oxidizing agent. Okay? Now we'll carry that over to organic chemistry. These hydride reagents, and they're typically metals or very close to metals, nonmetals, metalloids. They could be metals or it could be metalloids. If they have lots of hydrogens on them, what the metals tend to do is drive electron density out to the hydrogens. And that first one, lithium aluminum hydride, is a good example of that. We can throw the lithium out, right? Because we've been doing that before. And then what you end up with is or hydrogens that are especially negative. And if we want to simplify things, all we have to do is write that hydrogen as a hydrogen atom with an extra electron. Right? Normally, hydrogen atoms only have one electron. But from this reagent can produce the effect of a hydrogen anion. And that means it can donate electrons. It becomes the reducing agent. This one right here. It can donate electrons. So it's another nucleophile. Sodium borohydride, lithium aluminum hydride, those are both really good reducing agents. Okay, we're going to introduce this is actually the second elementary step. Let's see, we've covered one elementary step. Let's list them. First is the proton transfer. This one is called SN. Is it 2 subscript or 2? No, it's 2, but a big 2. Okay, what this means is it's bimolecular. Remember a bimolecular reaction in kinetics where you have 2 reactants come together. Okay, that's bimolecular. That's what the 2 stands for. The N stands for nucleophilic. So there's going to be some species that has extra electrons and is going to be looking for an electron poor reactant. And then S means there's going to be a substitution. In other words, the nucleophile is going to attack some part of the molecule, and as a consequence, something has to leave. That's a substitution. So let me write that out. This is a bimolecular nucleophilic substitution. Okay. Here's an example. And we've already seen this one, right? Where the hydroxyl, the base, and this, by the way, is also can lead us to Lewis base, right? A Bronsted-Lowry base is a proton acceptor, but it's also an electron pair donor because it donates an electron pair to form a bond with hydrogen. So the Lewis base then would be an electron pair donor. So that means if we go to any other molecule that donates an electron pair, that's a Lewis base. It's also a nucleophile. Okay. So we've seen that top one before. So let's look at the bottom one. What do we have on the bottom? Our nucleophile is an ammonia molecule. And nucleophiles can be charged, they can be neutral, but they always have available at least one lone pair of electrons. And in this case, the nucleophile is ammonia, and the substrate, which is the electrophile, the substrate is the one being attacked. Is this, don't ask me to name that molecule. I think I've got it on the next one or two slides. We've got a name for it. But what we want to look at now is the concept of the leaving group. For SN2 reactions, you need a leaving group. In other words, if you're going to do a substitution, something's got to leave the substrate. And what we want is the leaving group. It's the effectiveness, the ability of a group to leave the substrate is based upon where it ends up. Right? Is it very stable after it leaves? If it prefers that stability after it leaves, then that makes it a good leaving group. And on a subsequent slide, we're going to show you a bunch of examples and try to explain why each one is a good leaving group. But if we do that, then you see that the lone pair from ammonia attacks that carbon. And we're not saying a whole lot about the kinetics here. You know, is this a slow reaction or a fast reaction? Because you do have the bulk of that sulfur-containing group, and you do have the methyl groups there kind of getting in the way. So sliding that ammonia in there to attack the carbon might not be kinetically favorable. It might be a slow reaction, but it still would happen. So we attack the carbon. Now the carbon's already got four bonds to it, right? Two methyl groups, the hydrogen and the methyl sulfoxide, I think is what that's called. So it's already got four. So if we attack that carbon, we're trying to form a fifth bond, and that exceeds the octet, and you can't do that on carbon. Right? The second period elements, you can't exceed the octet because they don't have access to the d orbitals. So what happens is, this is a concerted reaction. We introduced that word last week. This is a concerted reaction where if you're attacking the carbon with that ammonia, then the bond has to break, and the electrons go to the leaving group. And the leaving group is stable for a number of reasons, but one of the primary reasons is it can resonate. Notice that negative charge can resonate around two other oxygens, and that does stabilize it. That makes it very stable for that extra charge. Even though we have put a positive charge on the amine group attached to the carbon, it's still very stable. Okay, this is another way to look at the reaction. Remember in kinetics, when you form a transition state, a bond is being broken and a bond is being formed at the same time. So we use dashed lines to show partial bond breaking and formation. That's what that nucleophile attached to the R group with a leaving group attached to it. This is a generalized reaction. Now, the only reason well, one of the main reasons that the reaction will proceed is that the energy difference gives you a more stable outcome. So this is an exothermic reaction. Even though you get a charge, you don't do away with a charge. And in fact, sometimes you create an extra charge, which you would consider would destabilize the situation. But the energy balance tells you that the reaction is favorable in a thermodynamic sense, right? If you look at the starting energy and the ending energy, that's where thermodynamics happens. Then it's more stable with products. If there's kinetic stability, then you need a very low activation energy. That may or may not be the case. Okay, but the whole point of this slide is to show you that the energy diagram favors formation of products, and you get those partial bonds breaking and forming. Now, what kind of substrate? The substrate is the one, of course, containing the leaving group. Now, in biochemistry, substrate has a slightly different meaning. I mean, there are similarities, but it's not exactly the same as organic chemistry. So we want a substrate that has that can form a relatively stable leaving group. Now, if it happens to be a negative charge, it's going to be more stable as an anion if we can have resonance or inductive stabilization. In this case, sulfur and oxygen is oxygen is more electronegative than sulfur, so it's not an inductive stabilization, so to speak. But it is resonance stabilized. Leaving groups are typically conjugate bases of strong acids. What does that mean? If you have a strong acid, like this, and we're going to break a rule and just say this. Which side is favored? That side. For a strong acid, this side is favored. And this is the acid. This is the conjugate base. So that conjugate base is very stable. That chloride ion is very stable. And chloride makes a good leaving group. Bromide makes a better one. But it's the conjugate base of a strong acid. Makes a good leaving group. The nucleophile says the nucleophile tends to be attracted by and form a bond to an atom that bears a partial or full positive charge. Now, does that carbon, if it's going to attack that carbon, does that point apply to this particular reaction? Is it a partial charge? Well, the carbon is generally neutral, but you do have oxygen as a withdrawing group. That oxygen is drawing electron density away from the carbon, and it does make the carbon slightly positive. Okay, moving on. So here's some examples of good nucleophiles. Right? An excellent nucleophile, one that is extremely strong, is hydroxyl ion. It's just the opposite of a leaving group. If you remember the I can't remember the words now. Water in pure solution does what? it transfers, say, a proton from here to here, and you get this hydroxyl. Let's see. That. And hydronium. Okay. Now, where does the equilibrium lie? The equilibrium lies way over here, right? Because the Kw equals 1 times 10 to the minus 14. It's way over here. What that means is this is a very weak acid. That makes this an extremely strong conjugate base. And strong bases, even in the Lewis sense, strong bases make extremely good nucleophiles. They're searching for some place to donate their electrons. And so they'll, if you put hydroxide in water, it will strip a hydrogen off a water molecule in a New York second. So that is that chart, that list of nucleophiles, probably hydroxyl is the strongest one. It might be a toss-up between that and the methoxy anion. The only way to tell is look at the K values. But these are all good negatively charged nucleophiles. Now, you can also have uncharged nucleophiles, and in order to have an uncharged nucleophile, you must have a lone pair of electrons. Now, the negative charged ones, they're going to have no lone pairs. That's a given. But the uncharged nucleophiles, you need lone pair electrons for them to be a useful nucleophile. Okay. Can methane act as a nucleophile in an SN2 step? Now let's look at methane. Methane is going to be like this, that. In a simplified drawing. We're not trying to imply any three-dimensional structure here. We're just looking at electrons. Would it be a good, right, there's your generic with the leaving group, right? You add that, is it going to be able to attack that R and cause this leaving group to go? Well, it's neutral, right? It's not charged. Does it have any lone pairs? Well, the difference between electronegativity between carbon and hydrogen is not that great. So you're not going to induce a partial negative charge on that hydrogen anyway. So, first question you asked, does methane have an atom that carries a partial or full negative charge? No. Does it have a lone pair of electrons? No. Neither one. So methane would not act as a nucleophile in an SN2 step. It just doesn't have the get up and go. Okay. How about this slide tries to compare a proton transfer to an SN2 reaction. Now, in my mind, proton transfer would be like a subset of SN2 reactions because you've got a nucleophilic attack, right? And you've got a leaving group. So in my mind, the proton transfer is just a different type of SN2. But if you don't have a proton transfer, then it's strictly SN2 and doesn't fit into that subcategory. And the hydroxyl attacking that methyl chloride is a good example. So you get the nucleophile, the hydroxide, it wants to give up a lone pair really bad. And it goes and attacks that carbon because the carbon now is electron deficient. Why is it electron deficient? Because chloride is more electronegative than carbon. It's drawing electrons, even though the bond is still covalent, it's drawing electron density away from that carbon and creating a partial positive charge at that carbon. So it makes carbon the electrophile, the substrate electrophile, and chloride is an extremely good leaving group. Why? Because it's the conjugate base of a strong acid. Okay, and their definitions I already put those on the board. All right. So let's see. We've got another example here. See if we can make sense of this one. Draw the SN2 step that would occur between, and this is just a proposition, occur between the, let's see, that would be a benzyl iodide, wouldn't it? All right, you've got a C6H5 is the benzene group, and it's not phenyl because it has another CH2 in between. So a benzyl iodide and the I guess methyl sulfide anion. Sodium, we can throw the sodium out. What that's going to give us is CH3 and then sulfur with a negative charge. And sulfur normally has 2, now it has 3 lone pair. It's like oxygen. I mean, it's in the same family. So you can treat it as if it's oxygen when you're trying to figure out how many lone pairs it has. And then we're going to add that to this molecule, which is, I'm going to draw the structure. It's easier to keep it straight in my head. And this is CH2 there. Okay. So which one is electron poor and which one's electron rich? This is obviously electron rich, right? So it's going to be the nucleophile. Now, is this a good candidate for an electrophile? Do we have a partial positive charge in here? Well, this phenyl group right here is going to be an electron withdrawing from the carbon, even though the iodine donates some. So which one is going to be the slightly positive? It's going to be this one, or is it going to be this one? All right, that's the question. Which one of those 2 carbons would be the most likely? All right, we've already done this part. We got rid of the sodium. Now we have a nucleophile. What about the substrate, though? We got a good leaving group in iodine, which means that it's probably going to attack this carbon right here, the carbon closest to the iodine. The carbon is attached to an electron, is electron poor because it's attached to the iodine. The iodine is drawing, wants electrons, it's drawing electrons away from this carbon. Okay, so that tells me that that's the electron deficient carbon. And the attack is going to come from here to there. And form a bond, with that carbon, with this carbon. So now we're going to have this group. We're going to have this carbon. And then we're going to have a sulfur here with a CH3 out there, like that. And we need, oh, I forgot the 2 curved arrows. Okay, we had to break this bond. When we form that bond, we have to break this bond. And there was a question, I think it was on the quiz. You know, is that arrow pointing to a lone pair? Or is it pointing to the atom? Well, arrows can never point to a lone pair. They have to point to an atom. If there are lone pairs in the way, you have to assume that it's pointing at the atom. All right. Is this making any sense so far? Yeah, I wish kind of yes and no. Okay. All right. These, I think I introduced these terms before. When a bond, let's say we have something here, right? We have the same one over here, but it doesn't have to be the same, but for illustration purposes. If these two electrons go to one side like that, this is called heterolysis. Hetero means other, and lysis means to break. So it's another breaking. And when we break that bond, both those electrons go to one or the other of the atoms. And I'll throw this one in here for now. Homolysis, just so that we'll be complete, goes both directions. So that's where we use a single barbed arrow. So one electron goes to Y, one goes to X, and we usually produce a free radical. But back with heterolysis. That's simple. When you let me see, I think back to general chemistry. When we were talking about forming bonds, usually one electron comes from one side and another electron comes from the other side. From the one atom donates an electron, the other one donates another electron. The simplest one is hydrogen. So if you have two hydrogen atoms coming together like that, when they form this bond, then each one has donated an electron to form that bond. And once the bond is formed, you can't tell how it was formed. A coordination bond is one in which electrons come from one side only. So if we get that, say that bromine, the Lewis base, the nucleophile is attacking the, let's see, what is that? Oh, that was 1, 2, 3. Well, it's a carbocation, but how did it get there? Well, it could have gotten there a number of ways. I'm trying to think of a name for it. That's a tertiary carbon. And if that was a hydrogen there before, we'd have a 2-methyl propane. But that doesn't mean that's where it came from. Anyway, that's the carbocation is the electrophile. And when the bond is formed, both electrons come from the bromine. So that's a coordination step where a bond is formed by donation of both electrons from one reactant. Well, the Lewis base, the nucleophile, donates both electrons. Another step below is offered, and the point of that slide is that the bond is formed by coordination, not by equal donation from both sides. Bond breaking, right? Coordination and heterolysis are like the flip sides of the same coin. you go one way with coordination, go the other way with heterolysis. And when the leaving group leaves, not always, but very often, you get the heterolysis step. All right. So we've looked at bimolecular nucleophilic substitution. Now we're going to look at addition and elimination steps. And actually, no, this is a different section. 7.3. Now we're in 7.4. So we're into nucleophilic addition and nucleophile elimination. Let me see. Is that worth putting up as a separate step? Yeah, I think it is. So we can have nucleophilic elimination. And nucleophilic addition. Addition is easier for me to wrap my head around. You're simply adding the nucleophile to the molecule. You're just forming the bond. And that's the first example there is the methyl anion, the carbanion of methane is attacking that carbon. Why does it attack that carbon? On the top one, top left. It attacks that carbon because the oxygen has withdrawn electrons from the carbon and made that bond polar. And the carbon now is electron deficient. So the anion, carbanion, attacks that carbon. Now, can it get away with it? Can we get that nucleophilic addition step? Is that valid? Well, yeah. We only have 4 bonds. All right, we had 4 bonds before. Now we have 4 bonds because when that nucleophile is added, the pi bond breaks with carbon and oxygen, and those electrons are sent to the oxygen. So we have a charged oxygen. We first had a charged carbanion. Now we have a charged oxygen. So we don't have any imbalance in charges. We started with 1, we got 1. Another example. Water can attack the acetyl chloride. Now, in this case, the chlorine and the oxygen are withdrawing electron density from that carbon, making it positive, a formal positive charge on the carbon. So the water can attack. Water is, in this case, is an acceptable nucleophile, and it forms a bond. Well, oxygen now has lost a lone pair, and that makes the oxygen positively charged, and the pi bond broke and sent its electrons to the other oxygen. And we have now, where we had no charges before, no complete charges, now we have a positive and a negative, but there's still balance. And what tells me that it's going to work, I'd have to see the energy diagram to see if this is energetically favorable. And then the last one, we get a hydroxyl attacking that methyl cyanide. In this case, the carbon is positively charged because the triple bond is has an effective electronegativity. And the nitrogen, no, the oxygen, nitrogen, carbon, yeah, nitrogen is more electronegative than carbon. So we get that added withdrawing effect from the nitrogen and the triple bond. So that's why the hydroxyl attacks. And the other factor to consider is the hydroxyl is extremely strong nucleophile. So even if you have a very weak electrophile, the strong nucleophile can take advantage of that fact. And in this case, we added the nucleophile. And we just had to break one of the pi bonds to the nitrogen. Now, in this case, we also have a balance of charge. The hydroxyl is negative and the product is negative. So on the right, you see a generic arrangement there. You have the nucleophile attacking some carbon that has a doubly bonded or a pi bonded group to it, or a pi bonded atom to it. That's the Z. And those pi bonds, the pi electrons are not as strongly held as sigma bonds. So they're easier to break. You can break the pi bond and send those electrons to the away from the bond that's being formed with the electrophile. Sometimes it forms a negative charge and sometimes it doesn't. Well, in these cases, every time it did, it formed a negative charge. Nucleophile elimination. That was a nucleophile addition. Elimination requires that, well, in this first example, you have 4 bonds to the carbon. That's okay. Now, did that come from the previous slide? I think it did. Yeah, there it is, the middle one. The middle one has a water attached to the carbon. No, it's different. Sorry, it's different. It's 2 methyl groups, not a water on there. All right, so we're beginning with a new substrate. But this molecule, if you have this molecule anywhere in the reaction sequence, then this is the most likely reaction that you're going to see, a nucleophile elimination. So the nucleophile is the chloride ion, but the molecule is going to eliminate it simply by moving a lone pair into a double bond with the carbon, and then you can't have 5 bonds with a carbon. So the most likely leaving group is the nucleophile, that is the chloride ion. That's one good rule to remember. How many bonds can atoms form? Right? Carbon tends to form 4 bonds if it's neutral. Can't form 5 bonds. It can have 3 bonds if it has a lone pair attached to it, right? Your carbanion. What about oxygen and sulfur? Oxygen and sulfur have 2 bonds. And usually lone pair electrons, 0 for this one. This one would have 2 lone pairs. Nitrogen can form 3 bonds with 1 lone pair. That's if it's not charged. Okay. Those just good rules to remember. It'll shorten the process. And let's see, halogens. Halogens, 1 bond and 3 lone pairs. Okay, nucleophilic elimination. Here again, you want the leaving group to be as stable as possible. That determines whether it's a good leaving group. So this OH2 with a plus charge makes a good leaving group. All you have to do is break the bonds. Now oxygen has its 2 pair of electrons and you've got a water molecule. Water molecule makes an excellent leaving group when you have it available. because it's very stable. Okay. Next, bimolecular elimination. This is E2. And the 2 stands for bimolecular, and E stands for elimination. These nucleophilic, this nucleophilic elimination, nucleophilic addition, let's see, let's go back. Nucleophilic addition, there's addition. Okay, so that's bimolecular. The nucleophilic addition is bimolecular. The nucleophilic elimination is unimolecular. It all happens with just one molecule. If you're looking for some patterns, this bimolecular elimination requires, and I think I can say always takes place when a strong base attacks a substrate where the leaving group is on a beta carbon. When we write terminology, we were at this cyclohexane, and we know that this one has at least one hydrogen on it. It actually has 2 hydrogens. But if we have a bromine attached here, like that, then the principal attack site for this hydroxyl, which is going to attack this hydrogen, right? And then the electrons from this hydrogen are transferred to this bond, and these electrons then are transferred to that bromine, and it leaves. So this is known here as the alpha carbon for this site, and this is known as the beta carbon. So when you have a hydrogen on the alpha carbon and a leaving group on the beta carbon, then you have the potential for a bimolecular elimination. All you need is a strong Lewis base. They call them adjacent carbons. I like the alpha beta because you're going to see it again later. Oh, there it is. I know I'd seen it somewhere before. These are more examples. You want a leaving group that's very stable. One of the things that also stabilizes a leaving group is for carbons, the stability of a carbon is increased. Let's see, let's go this direction. Increased stability. Increased stability of a carbon. Carbon compound as a leaving group is primary, secondary, tertiary, quaternary. So if your leaving group has 3 other carbons attached to it, then it's tertiary. And in this case, our leaving group is the one with nitrogen on it, that tertiary ammonium compound. And that stabilizes the molecule with those. Remember, the carbons, the methyl groups are electron donators. And nitrogen is more electronegative than carbon. So what you can get is stabilization through those 3 different bonds. And that makes the tertiary ammonium a good leaving group. So the electrophilic, the electrophilic, no, this is nucleophile, excuse me. This is still nucleophile. This is a bimolecular elimination. So we have the nucleophile attacking the, doesn't have to be a hydrogen, I don't think. Yeah, it does. excuse me, it does have to be a hydrogen, and it's on the alpha carbon, and the beta carbon is attached to the leaving group. So this is a generic. We still have the pair of carbons, hydrogens attached to one of them, and the leaving group attached to the other one. And typically, you form a pi bond as a consequence. Let's see, is that always the case? Appears to be. Electrophilic. Oh, this is a new one. Electrophilic addition. This is bimolecular elimination. This is kind of like a second cousin to nucleophilic. This is electrophilic elimination. Okay. So in this case, oh, wait a minute. Oh, they're going to do addition. But I don't have to rewrite it. So we're going to add an electrophile to the substrate. The substrate is the nucleophile. Now the electrophile is added to. In this case, the nucleophile is a nucleophile because it has pi electrons, and pi electrons are more loosely bound. That gives you the opportunity to use them to form a bond. In this case, this example, the electron poor has either a formal positive charge or a complete positive charge, and it's attacked by the pi bonds, the pi bond electrons. And that's how the bond is formed. Right? It forms, this is a coordination bond. Both electrons come from the pi electrons to form that bond. And very often what happens is you form a carbocation. But the carbocation is very unstable. What type of hybridization would you expect on that carbon? The carbocation. How many bonds does it have? It has 3. It's 3 bonded groups. That means it's sp2 hybridized. But it also has the positive charge. And it's highly unstable. So we're going to expect it to do something. It's going to have to do something to stabilize. So if you have a reaction in which you need a carbocation, you need an electrophile, like the carbocation. You can never go to the shelf and pull a carbocation off the shelf and use it. They have to be made in place in the reaction itself. Okay, so here we have more electrophilic addition. Right, we have this triple bonded carbon that's donating some pi bonds and making a bond with the hydrogen and breaking the bond between the hydrogen and the chloride. And the chloride, it favors that bond breaking because chloride is a very stable conjugate base of a strong acid. The hydrogen chloride is a strong acid. So that reaction is probably going to go. And then you have this unstable carbocation. Then the second example, you have benzene, just a pure benzene, and it can attack that nitrocation. Yeah, nitrocation. And that should also be unstable. So where do they come in? Carbocations and electrophile elimination. If you form a carbocation like that and it's unstable, then you can eliminate an electrophile. In other words, you can eliminate some leaving group becomes the electrophile, and it's takes the positive charge with it, and that stabilizes. In fact, it removes the carbocation and transfers that charge to the electrophile that's being eliminated. It's all the name of the game is stability. What's stable and what's not stable. Okay, other examples of electrophile elimination. You can also, talking about stability, you can stabilize a carbocation sometimes. If you want the carbocation to be longer lived than say a microsecond or a nanosecond, sometimes you can stabilize it if by forming the carbocation, you can get what's called a hydride shift or an alkyl shift within the molecule. The carbocation is one carbon, and right next door to it is a carbon with a free hydrogen. You can get that hydrogen to migrate to the other carbon. Now, how does it do that? Well, we're not really sure, but the electrons move to the carbon and they take the hydrogen with it. And that leaves a positive charge on the carbon that was originally bound to the hydrogen. That's a hydride shift. Notice what's happened in this particular example. Originally, the carbocation was on a secondary carbon. It had two carbons attached to it. But if we do the hydride shift, now the carbon is on a tertiary carbon. That is much, much more stable. That's what drives the reaction. This hydride shift is driven by stability. The outcome, the carbocation of the resulting carbocation is more stable than the original. Now, what do we mean by an alkyl shift? Well, we say alkyl because it could be a methane in this case. It could be a propyl group. It could be some alkane type group. It doesn't have to be a methyl group, but it can be. And if it is, we specify it as a methyl shift. But the alkyl shift can be more generalized. So again, if we move that positive charge, if we shift the methane over to the carbon where the positive charge is, and the positive charge is now on the other carbon, we get that same stability. So it can happen with the hydrogen or it can happen with this methyl group. Gives us more stable carbocation. I probably went too far with this one. I can't think of any examples of a quaternary, so let's stop at tertiary. Right, because tertiary would put a positive charge on a carbon that's bound to four other carbons, and that just doesn't, I don't think that ever happens. So when we talk about, actually at the beginning of general chemistry, talk about driving force. What drives a reaction to happen? You need something that drives the reaction, otherwise it's going to sit there. It's perfectly happy where it is. And we discussed several possible driving forces, but in general, the driving force for these reactions is an increased stability of the products. And what we mean by that is lower energy is more stable. So the products are at a lower energy level than the reactants. That stabilizes them. And what actually causes that driving force? You can have a charge stabilization, right? if you have, say you start off with charges in your reactants and you have no charges in the product, that's a stabilizing force, right? Because charge separation requires energy. And if you have a negative separated from a positive charge, to keep them apart requires energy. So when they get together and neutralize one another, you no longer have that requirement for energy to keep them apart. So the formation of this nucleophilic addition for that bromide to attack the carbocation stabilizes the molecule. Other factors in the proton transfer, this example, we have a negative charge at the beginning, we have a negative charge at the end. All right, so we can't say that we've stabilized it by neutralizing charges. We have the same charge before as after. But where is the negative charge located? The negative charge on that imidazide anion is more densely packed than it is on the chloride ion. Chloride is a much bigger atom, and it tends to spread the charge out and make it more diffuse, which stabilizes that negative charge. So what we say is the chloride can accommodate the negative charge better than the nitrogen. When you have a competition between charge stabilization and bond energy, the charge stability usually wins. So we didn't mention bond energy in any great degree. In this case, this particular example, the bond energy favors reactants. And we have to take the author's word for that one. But in this case, also the charge stability usually wins if there's a battle between the two. And we're going to get into a lot of that probably in the next term. Competing reactions, how to tell which one is favored. Here's another example. Charge stability favored over bond energy. Okay, so in this case, bond energy favors the reactants where you have hydroxyl attacking this ethyl chloride. And we're saying that it's an E2 reaction, so we're going to have a bimolecular elimination where the hydroxyl attacks that hydrogen that's on the alpha carbon, and the leaving group is on the beta carbon. Right? That produces a sigma bond with a hydroxyl that makes water, and a pi bond. The pi bond is less stable than the sigma bond. That's what we're saying. So the bond energy favors the reactants because the reactants have all sigma bonds. They're more stable. But the charge stability is better for the leaving group, the chloride, than it is for the nucleophile, the hydroxide. So this reaction is going to go. That's the short story. Okay, so here I kind of jumped the gun with carbocation and charge stability. These allyl cations. Allyl means that you've got a sigma bond right next to a sigma pi bond. So in this case, we can put the positive charge on either the first or the third carbon, and they will resonate back and forth between those two. Pronounce that word fast 3 times. Oxocarbenium ion. In this case, we've got an ether, methylpropyl ether. And it can resonate between the Well, let's see. That's a primary carbon on the left because there's only one carbon attached to it. But on the right, we've transferred the positive charge to the oxygen. And then the third example, right, which is more stable? Well, the more stable is where the benzyl cation puts the positive charge on the ring. And it has many other structures that can stabilize. It has two other possible structures for that carbocation on the benzyl. When we delocalize by resonance, we stabilize. So the allyl cation, the oxocarbenium ion, the benzyl cation, those are all stabilized by resonance. Now, what we're going to see in the future is when we see these resonance structures, you might see a different resonance structure on one side than the other. And one of those resonance structures might be more reactive. So at that point, it may continue its reaction with some other reactant simply because it resonates to that position and then it can go. But in the previous resonance structure, it wasn't able to react. So sometimes we use resonance structures to our advantage. We can produce a resonance structure. If we can do that and make one of those resonance structures reactive, then that facilitates a given reaction, elementary step in a reaction sequence. So here's carbocation stability, right? Methyl is very unstable and very unlikely, methyl carbocation. Where you have a primary, it's more stable. Where you have secondary, more stable. Tertiary is the most stable of the carbocations. Now, once we get past that, we also find that the allyl carbocation is about as stable as the secondary carbocation, and it's stabilized by resonance. And the tertiary is about as stable as the oxycarbenium and the benzyl. Okay, which side of this carbocation rearrangement is favored? I think it's fairly obvious if we just look at the rules. The one on the left is a tertiary carbocation, right? The one on the right is a secondary. So the methyl shift, the 1,2 methyl shift on this cyclohexane is not likely to occur, or less likely. In other words, it may occur, but the predominant species is going to be the one on the left. You probably will get a few on the right simply by chance. But the most stable one is the one on the left. All right. We're favoring the reactant side in this case. So what do we mean by hyperconjugation? All right, say we have a methyl carbocation there, an A, which means that we've got a sp2 hybridized. So this CH3 carbocation. Now that implies that the charge is on the hydrogens. We better put it over here. That primary means that this carbon is sp2 hybridized. If we have a, let's see. Well, what's under B? What molecule is that? Oh, okay. If we have instead, we have this here attached to, let's see, this is a 2, I think. Yeah, only 2 hydrogens here. two hydrogens here, and this is attached to a sp3 hybridized. So this is sp3, and this is still sp2 hybridized. Then we have, say, one of these hydrogens. Let me draw it like they drew it. They did two here, and then they sent this one up here with the hydrogen. And this unused p orbital is where the positive charge resides. That doesn't make any sense because you can't have a positive charge without absence of electrons. So there's nothing there really. So what we're saying is we're trying to explain why the secondary carbon is carbocation is more stable than the primary. And if we draw the molecular orbitals for this molecule, we find that both electrons now from the bond to the hydrogen now reside in a lower molecular orbital. I think that's what we're trying to show. That delta E, the red arrow, is the energy difference between this hyperconjugation producing a molecular orbital that is much lower in energy. And that's where both electrons reside. And that lowering energy stabilizes. Okay. That can be carried further with the tertiary also. You can get a further lowering of the energy of the molecular orbital. Remember, molecular orbitals are, I think we covered this already. They're like chemical communism. The electrons belong to everybody. Okay, so here's another way to stabilize a molecule. We get a keto-enol. This is called tautomerization. So remember what a keto is, right? Ketone is this carbon with a carbonyl group on it. And this would have to be some R group other than hydrogen. Okay. This is the alpha carbon. And this will have, three hydrogens. Now, we can have this. Right? This is possible. You can have longer chains out here and still a ketone. But what's an enol? Right? This is a ketone. And we have one of these is a hydrogen. Then we can form, let's see, we get a hydrogen shift. We get a hydride shift to that oxygen, and the double bond now resides on these two carbons. And now instead we have hydroxyl there. So this hydrogen moved to that oxygen. That's a keto-enol tautomerization. Now we got to decide which one is more stable, because that's where we're headed. These isomers are isomers of each other, right? Because they have the same molecular formula, but they have different structures. So they're definitely isomers of one another. You have to have a hydrogen on the alpha carbon next to the beta carbon where you have the carbonyl. And then with the transfer of that hydrogen, you get a double bond between the carbons and the alcohol. Okay. I think this is, this is the mechanism. So first of all, what we're going to do is we're going to produce a carbanion. And the carbanion we take the ketone and we extract that. We do a proton transfer from the substrate to the hydroxyl and make a water molecule. And then that gives us a carbanion. And that shift occurs where the negative charge that was here now moves up here. And they resonate between each other. And then the enol now is a strong nucleophile. And it attacks the hydrogen that was transferred to that water molecule. And now we get the enol by proton transfer. So you get 2 proton transfers, and you can convert a keto to an enol. That was under basic conditions. What about acidic conditions? It's a different mechanism. Now the keto is the nucleophile, right? And it attacks the one of the hydrogens on the hydronium ion. That makes a positively charged oxygen, which is not good because oxygen now has 3 bonds. You can't have that. So the bond, and this is probably concerted, the bond breaks and forms the alcohol. And now the water, now that you have a carbocation, because you've reduced the number of bonds on that carbon to 3, now you have a carbocation, and the water attacks that alpha, not the alpha. It attacks the hydrogen. And the electrons there are transferred into the double bond. So you end up with the same product, but you undergo that reaction under basic or acidic conditions. And whether or not you use basic or acidic conditions depends on where you're headed with the reaction. If further steps need to be in basic environment, then you'll want the top one. If further steps or steps where it came from are acidic, then you'll want the acidic condition. So you have those 2 opportunities. All right. I thought we already did that one. It's making, what is it doing? Enolate anion? Looks like it's going backwards. Oh, that is the reverse reaction. All right, it can go backwards. Yep. Those reactions can go backwards. Big surprise there, huh? Reverse reactions are always possible. And actually, that was that one of the questions on the quiz? Maybe it wasn't. These arrow pushing requires that the elementary steps, the movement of electrons, are reversible. Well, we know that's never going to happen, but theoretically, they're reversible. Okay. This table says something about the relative percentages of the ketone and enol forms, and it depends on what else is in the environment, right? If your ketone is on a secondary carbon and there's nothing but hydrogens around it, then you're going to get predominantly the ketone, and the enol is not going to be favored. You can produce a little more of the enol if you add carbons to the hydrogen bound to the hydrogen side. Let's see. Now, if you put a carb, oh, wow. So what's the most stable one? There must be more to this chart. No, there's not. It looks to me like the stabilization of this tautomerization is favored toward the keto. Keto is more stable no matter what you do, but some are more stable than others. Probably the one that produces the most enol is the tertiary carbon stabilized for the hydrogen. That's the one that's going to give you the most enol product. But enol in general is unstable. All right. And this slide just demonstrates with the bond energies that the keto group is more stable. I think we'll move on from that. Okay, tautomerization in your body. All right. Nobody in here has been introduced to biochemical pathways, right? Okay. Glycolysis is generalized the first step in the use of sugars. And it's anaerobic. It occurs without the presence of oxygen. So when you exercise, especially if you haven't exercised for a while and you exercise and your muscles the next day are sore, that's because your body has undergone a glycolytic pathway in excess. And the one that requires oxygen would take the products all the way to carbon dioxide and water and give you more energy. But if you're stressing the muscles too much, then they only have the anaerobic pathway available to them, and they produce lactic acid as a byproduct. And that's what makes your muscles sore. But glycolysis is the starting point for breakdown of the simple sugars. One on the left is glucose, one on the right is fructose, and you don't have to know. The molecule is activated by phosphorylation, right? It needs that before it can undergo the reaction. So that's something you get later if you go into biochemistry. Right now, it's not important. What we're looking at is the tautomerization of the molecule. In order to happen, the molecule has to open up, right? The top one is a ring structure. It's that's the chair model for glucose. And it has to open up in order to produce the tautomerization. I don't think we're going to spend a lot of time on it. Except to say, glucose, you'll see, which glucose is this? The OH is on the right. That's D-glucose, isn't it? I think it is. Okay, well, that's enough.